In this video, we are showing why you need hybrid CTLE to achieve a less residual RSI or a bigger equalized eye opening. But what is the hybrid CTLE? Think about the images of the passive and active CTLEs for 5 seconds. Correct. Last time, we discussed the impaired images of the passive CTLE and active CTLE respectively. That motivates people to choose one but not the other. Instead of looking at their impairments, can we look at both advantages and combine them to be a hybrid CTLE to achieve the best equalization performance? If your answer is yes, then we should look at the strength images of the passive and active CTLE respectively shown below. The first strength of the passive CTLE is that we can independently adjust the values of the R1, R2, C1, and C2 to decouple the dependency of the tuned DC attenuation, high frequency attenuation, peaking gain, 0, and pole frequencies from each other. Therefore, the passive CTLE's high pass response may have more flexibility or tunability to be the inverse of the channel's low pass response property with less variability over PVT. In addition, the passive CTLEs will not only have an intrinsic good linearity, but also have a high tolerance of the input swing and impairments of the input common mode voltage. On the other hand, the active CTLE's AC gain will provide a high input sensitivity and great signal-to-noise ratio for the sampler's proper timing at a very high data rate and great noise immunity at a very low bit error target. Lastly, the good input sensitivity and signal-to-noise ratio provided by the active CTLE could also allow the TX to send a small swing with a low power state such that the whole power in a link can be reduced. From those strength images, do we have any idea how to combine both CTLEs together? Think about the tolerance images of the input impairments for 5 seconds. Great. The passive CTLE has a high tolerance for the input swing and impairments of the input common mode voltage. In addition, the sampler's input sensitivity and SNR can still be enhanced even though the active CTLE is not at the first stage. Therefore, we may want to put the passive CTLE first and the active CTLE in the following stage. Lastly, in advanced technology, it's difficult to get much more AC gain at a very high speed operation. Sometimes, multiple cascaded active CTLE are needed to meet the required AC gain or input sensitivity for the sampler. Alright, is that all? Think about the input matching images for 5 seconds. Bingo! We need to add the input matching property since the frequency response of the CTLE input will be part of the whole equalizer's AC response. Therefore, we add the whole RX front-end circuit images here to remind you the designs or verifications must be done together to avoid the missing mistakes. What's the subtle images here? Think about the image of bottom plate capacitance for 5 seconds. Correct. The feed-forward capacitance C1 was made by any two metal layers, but those two metal layers would have the parasitic capacitance coupled to the ground layer. Even though the T-coil can mitigate those parasitic, the main purpose of the T-coil is to mitigate the extra capacitance from the ESD. Therefore, we still don't want the CTLE's input capacitance lose the central top ESD of the T-coil too much. In addition to the input matching, what else could be the issue if the C1 contributes too much parasitic capacitance to the ground? Bingo! The C1's other side could contribute more capacitance on the C2, which may affect the high frequency attenuation and the peaking gain. So we must watch out for any parasitic capacitance of C1 to the ground path to make sure both the input matching and equalization accuracy were good enough. After knowing the impact of the extra capacitance from the passive CTLE, think about the extra resistance image for 5 seconds. Right, if the R1 and R2 are too little, then the resistance will reduce the input impedance at low frequency, since it's in pair with the termination resistor. Therefore, we suggested the resistance for the R1 and R2 should be greater than 500 ohm single-ended, which should ensure less than 10% degradation in the input termination 50 ohm single-ended. Is this good enough? Think about the switch images for 5 seconds. Not yet, and unfortunately, as we mentioned, we can independently adjust the values of the R1, R2, C1, and C2, but we must add the switches in series with R1, R2, C1, and C2. We could make the resistance of the switch less than 10% of the R1 and R2, but the parasitic capacitance could be too big to achieve an accurate AC response. On the other hand, we could make the switch in series with the C1 big enough, which would not lower the C1's capacitance value too much, but the extra capacitance from the switch would add another issue that the C1's parasitic capacitance we just discussed. Therefore, we must take advantage of the available ultra-low threshold voltage device, ULVT, in the most advanced technology to size the switch properly in the trade-offs between parasitic resistance and capacitance. Here is the summarized image of why we need a hybrid CTLE. We've known the corresponding advantages image of the active and passive CTLE respectively. Why don't we combine both advantages by putting both CTLE together to achieve the best equalization performance? First, the passive CTLE has a high tolerance for input swing and impairments of the input countable voltage. Second, the sampler's input sensitivity and SNR can still be improved if the active CTLE is not at the first stage. Therefore, the hybrid CTLE is to put the passive CTLE first and active CTLEs in the following stages. Unfortunately, the first stage passive CTLE must co-design with the RX input matching with the T-coil and RX termination. First, the parasitic capacitance from the 54-volt capacitor C1 and shunt capacitor C2 must be reduced to avoid loading the ESD node and degrading the equalization accuracy. Second, the R1 and R2 must be big enough without loading the X termination, fitting almost single-ended too much, and both resistance greater than 500 ohms are better. Lastly, to adjust the values of the R1, R2, C1, and C2 independently, we must add the switches in series with them, but the switch size will be trade-off the parasitic resistance and parasitic capacitance. Hopefully, we could take advantage of the available ultra-low threshold voltage device, ULVT, in the most advanced technology to size the switch properly. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.